I welcome you all to my YouTube channel Insight into Chemical Engineering. In this lecture series, we will solve the unsolved problem of a famous book, Stoichiometry and Process Calculations by K.V. Narayanan. These lectures are helpful for chemical engineering students because it is a core subject for chemical engineering branch. During lecture, step-by-step solution will be provided. In this lecture, exercise number 5.5 to 5.7 will be covered. Please like and subscribe for motivation. Problem number 5.5. Calculate the pressure exerted by 1 mole gaseous ammonia contained in a vessel of volume 0.03 meter cube at a temperature of 340 Kelvin using Radlich-Koch equation of states. The critical constants of ammonia are 405.5 K and 112.8 bar. Then compare the result with the value obtained using the ideal gas equation. So here we need to use Radlich-Koch equation, then we will compare the result using ideal gas equation. So first we will write Radlich-Koch equation. So as per Radlich-Koch equation, pressure is expressed as P equal to RT divided by Vm minus B minus A divided by T raised to power 0.5 into Vm plus B, and further values of A and B are expressed in terms of critical temperature and pressure. Now in the problem, volume is given, number of moles is also given, that is 1 mole, temperature is given, and the critical values temperature, Tc and Pc are given. So by putting the values of Tc and Pc, we can find out the values of constant, that is A and B. So in this equation, this Vm is the molar volume, that is volume per unit mole. So we can find out the pressure because all parameters are known, temperature is known, molar volume is known, A and B are known, temperature is known. So first we will write moles of NH3 equal to 1 mole. So first we will find out this molar volume. So molar volume is volume per unit mole. So volume is given, that is 0.03 meter cube divided by number of mole is 1. So it will become molar volume, that is meter cube per mole. Now we can find out the values of A and B by putting the values of critical parameters. So after putting all values, we will get the value of A, that is 8.674. So we can also find out the value of B, and value of B will come out as 2.596 into 10 raised to power minus 5. So this is the first term. So here the pressure is expressed in this form. So what we will do, first we will calculate this first term, that is RT divided by Vm minus B. then we will find out this second term, then we can take the difference. So here simply we will put the values of R, T, Vm and B. So after putting all values, we will get this much. Now we can find out this parameter, that is A divided by T raised to power 0.5 Vm into Vm plus B. So after putting all values, we will get 522.23 Pascal. So we have estimated these two terms. Now we can take the difference. So we will get pressure. So pressure will become this term minus this term. So we will get 0.938 bar. So this is the pressure that we have estimated using Redlich-Kwong equation. Now we need to estimate the pressure using ideal gas equation. So one thing is confirmed, when we will use this ideal gas equation, so estimated pressure will come more than this pressure, because in ideal gas we do not consider van der Waals interactions. So we can find the pressure using ideal gas equation using PV equal to nRT equation. So we can write P equal to nRT by V, and after putting all values we will get 0.942 bar. So we can observe that the pressure estimated using ideal gas equation is more than the Redlich-Kwong equation. Problem number 5.6. Ethylene at 500 bar and 375 Kelvin is contained in a cylinder of volume 0.03 meter cube. The critical properties of ethylene are given. Now we need to find how many kilograms of ethylene are there in the cylinder using van der Waals equation. So here we need to find out weight of ethylene. So anyhow we have to estimate the moles of ethylene, and everything is given, that is pressure is given, temperature is given, volume is given, and critical temperature and pressure are also given. So using van der Waals equation we can easily find out the number of moles. So first we will write the van der Waals equation. So that is P plus AN square divided by V square into V minus NB equal to nRT, where A and B are given in terms of critical temperature and pressure. So we can find out the values of A and B by putting the values of critical temperature and pressure. So after putting the values we will get the value of A. In the same way we can find out the value of B. Now what we can do, we can express the above equation in terms of molar volume. Molar volume is simply, that is volume per unit mole. So here we have volume V square, here we have number of moles N square. So we will take this N square below this V square. So it will be V square by N square. then V by N can be written as Vm. So we have just divided this whole term by this N. So after dividing this whole term by N equal to RT. So we will take this N in this bracket. So when this N will go inside this bracket, then it will be V by N and this N will get cancelled. So we will get P plus A N square divided by V square into V divided by N minus B equal to RT. Now we can write V by N as Vm. So finally we can express this equation in terms of volume. So after multiplication and rearranging, we will get this equation in terms of volume, and it will come as V raised to power 3. So that is the cubic equation in volume. Now we can put all values. We can put the values of B, R, T, P, A, P, A, B and P. After putting all values, we can solve this equation and we will get 3 roots. Out of 3 roots, we can take the real roots. So in next slide, we will solve it. So after putting all values, we will get this equation. Now we can simplify. So after simplifications, we will get this equation. Now we can go to this website, so where we will put the coefficients of Vm cube, Vm square, Vm and constant, and we will get the values of Vm. So using this website, we can solve this equation and we will get 3 values of Vm. And out of 3 values, we have to consider the real root of Vm. So Vm will come out as 8.65 into 10 raised to power minus 5 meter cube per mole. Now we can write Vm is molar volume, that is volume per unit mole. So already volume is given in the problem, so we can find out the moles, and Vm we have already calculated. So number of moles will come out as 346.82 mole. Now we can convert these moles to weight. So weight of ethylene will be equal to moles into its molecular weight, and it will come out as 9.71 kg. Problem number 5.7. A fire extinguisher of capacity 0.04 meter cube contains CO2 at certain temperature and pressure. Now it is to be charged with CO2 to a pressure of 20 bar at constant temperature of 300 Kelvin. Determine the kilograms of gas to be admitted assuming van der Waals equation, and critical constants are given. So first we will try to understand the problem. So in the problem we have a fire extinguisher. It contains CO2. So at initial state, it is given that pressure inside this extinguisher is 101.3 kilopascal. Also the volume is mentioned, that is 0.04 meter cube, and temperature is also mentioned, that is 300 Kelvin. But we don't know the initial number of moles of CO2. It means N1 is not known. But here we have to use van der Waals equation. Otherwise, simply by using PV equal to nRT, we would have calculated N1. But here we will use van der Waals equation. And whenever we use van der Waals equation, so it is advisable to use this equation in terms of molar volume. Now further, this extinguisher is charged with CO2. So if we will add more amount of CO2 inside this, then what will happen? The pressure will change. But in problem it is given that temperature is constant. So temperature will remain same, only pressure will increase and volume will also remain same. So at state 2, volume will remain same as it is. Temperature, there is no change in temperature, only the pressure will increase and pressure is given, that is 20 bar. So number of moles at the final state we don't know. So that is the state number 2. So basically we need to find that how much kilogram of CO2 we are charging or we are admitting to this extinguisher. For that, anyhow, if we can find out the initial number of moles and final number of moles, then we can take the difference. The difference will give the number of moles of CO2 charged. But here we have to use the van der Waals equation. So using van der Waals equation, we will find out N1 and N2. So first we will write the van der Waals equation. So this is the van der Waals equation. So parameter A and B are given in terms of critical temperature and pressure. So in the problem, critical temperature and pressure are given. So we can estimate A and B. So by putting the values of TC and PC, we have estimated A. In the same way, we can estimate B. Now, in next slide, we will express this equation in terms of molar volume. Then we will plug in all values and we will find out the value of molar volume. Then molar volume can be written as volume divided by moles. So from there we can calculate the N1. So we are expressing van der Waals equation in terms of molar volume. So in terms of molar volume, we can write this equation in this form. Now we will simply put the all known values, that is B, R, T, P and A divided by P, A, B and P. All these coefficients are known. And we need to estimate this at the initial conditions, that is at the state 1. So we will use these parameters, that is pressure, volume, temperature at state 1. So after putting all values, we will simplify this equation, and after simplification we will get this equation. So this is the cubic equation in terms of molar volume. So again, using this website, we will put the coefficient of volume V cube, Vm cube, Vm square, Vm and the constant. So after putting all coefficients, we will get the three different values. So we will take the help of this website and we will get molar volume equal to this much. Now we can write this molar volume as volume divided by moles. So we can find out the initial moles of CO2, that is N1. So after putting the values of volume, that is 0.04 meter cube, and Vm we have just estimated. So just by dividing V by Vm, we will get the number of moles of CO2. And in next slide, we will find the same number of moles at different conditions. That is at state 2. So at final condition, that is the state 2. At state 2, pressure is different. So we will rewrite the van der Waals equation. So we have expressed this equation in terms of cubic form. Now we will plug in all values. So we will get this equation. So this time only the pressure is different. So that is 20 bar. So here we have written P is there. So here we will write 20 into 10 raised to power 5, because we need to convert this pressure to Pascal. So after simplification, we will get this equation. Now again, using that website, we can find out, we can solve this equation. So after solving, we will get the molar volume. So this is the molar volume that we will get. Now we can write molar volume equal to volume divided by number of moles. So from there we can find out the final moles of CO2, that is N2. So it will come out as 35.242 mole. Now we can take the difference of final moles minus initial moles. So moles of CO2 admitted to cylinder equal to final moles minus initial moles. So this is the final moles that we got, and this is the initial moles that we have estimated in the previous slide. So this is the moles of CO2 which are admitted to the extinguisher. So we can find out the weight of CO2 equal to moles of CO2 into its molecular weight, and it will come out as 1.478 kg.